Let's continue with this idea of self-similarity. In fact, let's take it another step. In this lecture, we're going to look at what we call approximate self-similarity. This is one of several dichotomies that you'll read about in the textbook regarding self-similarity. The first of these two is the contrast between local self-similarity and universal self-similarity. On the left, we see a package of cocoa. This is Droste cocoa, or Droste. I'm not quite sure about how to pronounce it. It actually gives its name to an effect. You can look this up in Wikipedia, for example. And it's this idea of inside a picture, inserting at a realistic place a smaller copy of the same picture itself, where it would naturally occur. But what I want to point out is, in this self-similarity that we see in this cocoa box on the left, it's only really occurring at one place. So the only place where we see the self-similarity is if within the big picture we look at the cocoa box and then see, oh, on the face of the cocoa box there is a copy of the entire picture again itself. And then, of course, there's a picture within the picture and a picture within the picture and so on, continuing for as far as we can imagine, or more realistically, till we reach the resolution of the ink that's being used. But when I say it's local self-similarity, there's only really one place we can point to where we see the self-similarity, namely the box of cocoa within the picture. On the other hand, if we look at the Koch curve, as shown here, this has universal self-similarity, by which I mean no matter where we look at it, look at any place on the Koch curve, we see a smaller version of the Koch curve. So that's universal self-similarity. Well, there's also the dichotomy between exact self-similarity and approximate self-similarity. The Koch curve has exact self-similarity. That is to say, if we look at some small piece of the Koch curve, we see just a scaled-down copy of the entire Koch curve. We've also talked about generating using some randomness, something like the Koch curve, where we start with a line segment and then replace it by 4 smaller segments, but we use a die. We roll a die so as to decide whether to make that pointy new shape that we're inserting go to the left or go to the right. And we do that at every stage. So we don't expect that we're going to see an exact copy of this fractal if we look more closely. What we do see is we kind of see a fractal looking the same way in rather a more vague sense, having the same sort of properties, the same kind of jaggedness. So again, on the left we have exact self-similarity, on the right approximate self-similarity. These mathematical objects that we're dealing with, these are theoretical constructions, so they really have self-similarity to all levels. So here is the Sierpinski carpet, and you can see that the Sierpinski carpet is self-similar. In fact, it's exactly self-similar. It's made up of 8 copies of itself, arranged around a black hole in the middle, a place where there's no copy. Okay? But also, we can look down to smaller scales. So it's true that if we look down at 1/3 scale, we see a copy of the entire carpet. But if we look at it 1/3 of 1/3, we look at an even smaller piece of it, we see, again, a copy of the Sierpinski carpet. And this continues to every level, theoretically. In our pictures, of course, we can't draw this. There's a limit to the resolution of our pictures. But in theory, these mathematical objects, these theoretical objects, have infinite self-similarity. Now, if over on the right we look at the broccoli, well, clearly that doesn't have infinite self-similarity. It has self-similarity at 2 or 3 scales, and then no further. It certainly doesn't have self-similarity down to the molecular level. The molecules of broccoli are not broccoli molecules. So, just to try this out in a couple of examples, here is the cover of the Pink Floyd album Ummagumma. It has local, finite, approximate self-similarity. That is to say, first of all, the self-similarity that we're seeing is not global. If we look at the trees in the background, we're not seeing a smaller copy of the album cover. It's only when we look at the picture in the wall that we see the album cover repeated. And then inside of that, again, we see something hanging on a wall, and it's a copy of the album cover. But it's only approximate self-similarity because if you look closely, you'll note, wait a minute, it's not really the same photograph that we're seeing. It's pretty much the same, but the members of the band have rearranged themselves. They put themselves in new positions before taking a photograph that's not quite the same as the original. On the other hand, what can we say about the Sierpinski carpet? Well, it's universal self-similarity, it's infinite self-similarity, that is to say at all levels, and it's exact self-similarity. Now, to finish off this lecture, I want to look at something called the Mandelbrot set. If this were going to be a longer piece of the course, instead of 3 weeks, 3 units, we would probably get to the Mandelbrot set. There is material about the Mandelbrot set in our textbook, and it would be a very interesting thing to do. But since we're doing just 3 weeks on this topic, we've decided we're not going to look at the Mandelbrot set, except very briefly in this lecture. As I say, it's described in the book. You could look in section 13.4 of our textbook, but that's not assigned, and you don't have to do that. The reason that we're not going to do it is that it would take us probably a good chunk of a week to understand about complex numbers. Maybe you've heard about complex numbers. So this is where you start with the square root of -1. You call that number I. You form things of the form A plus BI. You learn how to do arithmetic with them. That's complex numbers. And you have to study that and understand that before you begin to talk about the Mandelbrot set. So we won't do that. But let me assure you, it's a very simple definition. It's not very much more complicated than the kind of definitions we've been using in our other fractals thus far, our Koch curve and Sierpinski gasket and so on. Now, this has universal self-similarity, infinite self-similarity, that is to say at all levels, but it's approximate self-similarity. So what I'm telling you is, if you zoom in on the Mandelbrot set, you will begin to see things that again look like the Mandelbrot set, but not exactly the same. You'll see pieces recurring. You'll see other pieces that look like you've seen them before, but they're distorted, and so on. So it's approximate self-similarity. This is an object that was discovered in the 20th century. It was first defined in 1978 by Brooks and Metelsky. They didn't really have a very good picture of it, and I think they wanted a picture of it because it seemed like it would be an interesting object to visualize. It was visualized on an IBM mainframe computer in 1980 by Benoit Mandelbrot, who's shown down there, French mathematician who died not long ago in this century. And he really popularized the subject of fractals. In fact, his name's been mentioned before. He's the one who invented the term fractal. Again, to finish off, I'd like to ask you to go look at a video. There is a link from our Carmen page to view a video, which is called Zooming In on the Mandelbrot Set. I think you'll find it's mesmerizing. Now, this is something like a 9-minute video. There's no reason to actually look at the whole thing. So just look at it for as long as you like, and I hope you're awed and mystified by the extreme complications and beauty of the Mandelbrot set.